Here's today's starter. Pause the video and have a go at the questions. I'm going to reveal the answers now. Today we're going to complete numerical integration by finishing off our look at the trapezium rule. Here are some questions that you looked at yesterday from exercise 15b. When you look at those integrals, how do you know that your trapezium rule is going to give you an underestimate or an overestimate of the exact value of the integral? To find out, we use the same strategy as we did with the rectangles. We simply sketch a graph. Let's have a look at these ones. So here we can see that for our first trapezia it lies below the curve, and so that would give us an underestimate of the integral, but the second integral lies above the curve and we don't know how much above and below, and so that means that we can't really tell what's going on with this graph. Part of the trapezium rule will give us an underestimate, but part of it will give us an overestimate, and that sometimes happens with the trapezium rule. It really depends on how the graph itself is curved. For our second graph, we have the same problem. So the first trapezia is nice and obviously underneath the curve, so that's an underestimate, but the third trapezia and the fourth trapezia lie above the curve, so they give us an overestimate, so we can't tell altogether what will happen. For this third example though, we can see that every straight line at the top of the trapezia is going to lie beneath the curve. So the curve kind of bulges above it. So this one is definitely going to give us an underestimate of the true integral. If we look at the curve here, it's always curving downwards. Okay, whereas if we go back to the first example, on this part of the graph it's curving downwards, the gradient's decreasing, but then it flips over and starts to curve upwards, the gradient's increasing. For this example, it's like the third one. The curve itself is always curving downwards again, but we can hardly see whether the straight lines lie below or above the curve. But if you imagine a curve curving downwards, it's going to bulge on the outside, so the trapezia will lie underneath. They are going to be underestimates, so we'll have an overall underestimate of the integral. We have the same situation, or something that looks very similar, for this example here. And for our final example, we can see that the curve is always curving upwards here, and that the trapezia therefore extend above the curve. These straight lines lie above the curve, so our trapezia are always overestimating for this example, and so overall the trapezium rule is going to give us an overestimate of this integral. So from the graphs we can see that if the tops of the trapezia lie beyond the curve, then the trapezium rule is going to give an overestimate for the integral, only if that's true for every trapezia in the graph. This is always going to happen if our curve curves upwards, so we've got a gradually increasing gradient. This is called a convex curve, and you'll learn a lot more about curvature in Year 13. However, if the trapezia lie beneath the curve, so then we're going to get an underestimate of the overall integral. That has to be true for every trapezia to be able to tell that we're going to get an underestimate of the integral. This always happens when the curve itself is curving downwards. So if the gradient of the graph is always decreasing, we have a downwards curve, and we call that concave. Again, you'll learn more about convex and concave later in Year 13. The way I remember concave is a little cave with a bell in it. For this curve, we can see that the curve curves downwards and then it curves upwards. So that means that some trapezia are lying below the curve and some trapezia are lying above the curve. So overall, we can't tell if the trapezium rule is going to give us an over or an underestimate of the integral. So what I'd like you to do now is you're going to be presented with a graph, and I want you to decide whether it will give you an overestimate for the range given, or an underestimate of the integral for the range given, or if you can't tell, or if you'll get an exact match. Here's the first one. So you can see we've got a bit of curving downwards followed by curving upwards, so we can't tell in this situation. On this graph, the curve is always curving downwards, so our trapezia is going to lie straight across beneath that, so it will give us an underestimate of the integral. This graph is very wiggly. You can see it's curving downwards and curving upwards, so our trapezia are going to lie above and below, so we can't tell. On this curve, we can see that the graph is gradually curving upwards. It's getting less steep. Our trapezia, if you imagine joining up the two tops of the lines, then they're going to join up above the curve. So our trapezium rule is going to overestimate the integral. This one is a trapezium, so it's perfect. This time we've got equal amounts of curving upwards and curving downwards. So that means our trapezia are going to cancel each other out on the overestimating and underestimating. So I wouldn't do this unless you knew for absolute definite that you've got exactly the same area but above and below, but we're going to get a perfect match, which in fact the area would be positive, but the integral would be 0. On this part of the graph, we can see that we're curving upwards. So that means the trapezia is going to lie above the curve, and we will be overestimating the integral. So, do you think it depends on which part of the curve we're looking at? Well, we used graph 4 twice here, and one time it gave us an underestimate, and one time it gave us an overestimate, and it simply depended on which part of the graph we were looking at, because that told us whether the graph was curving downwards or upwards. Does it depend on how many intervals there are? Well, it shouldn't do. It should only depend on the curvature. If you're looking at a graph that goes below the x-axis, be really careful of the wording of the question. So, we can see that this curves upwards, it's convex, which would suggest to us, normally, that we get an overestimate. Now, we do get an overestimate because it's more positive than sum of our trapezia is more positive than the integral, but the thing we tend to look at, and is most commonly asked in a question, is whether we're over or underestimating the area between the curve and the graph. And here we can see that the blue trapezium area is much smaller than the pink curved integral area. So we've definitely got an underestimate. Here's an example the other way around. So this graph is curving gradually downwards. It's a concave graph. And from before, we suggested that graphs that curve downwards, we get an underestimate for. Now we do get an underestimate of the integral, which will be negative. So our trapezia are going to give us a more negative result than the integral would. So we are underestimating there. However, we don't normally think about that. Looking at the picture, we can see that our trapezia area are going to overestimate the area between the curve and the graph. Here's a question for us to try then. So we're going to start with a trapezium rule to estimate the area of R. Let's write down our key information first. So we are going from 0 to 3. We're told we're going to use 3 strips of equal width. We can calculate that width using our formula for h. So that's just 1. We then quote and substitute into the formula. So I've substituted in my x's into my formula for y. Okay, I worked out my x's because it's just 0, 1, 2, 3, which is fairly straightforward, and just pop them in. Then I've used my calculator to work out what my y's will be to make my life easier on the next bit. Type that in and I got 6.18. Then it's a very good idea to check on your calculator using the integral function if that seems sensible. For part B, we're going to try and decide if our estimate using the trapezium rule will give us an over or an underestimate. An easy way to check this is to simply join up one end of the curve to the other for the region we're looking at. Our strips will be similar to that, but we can't see them as easily. So we can see that our trapezia are lying above the curve, so we have an overestimate. We can always improve the approximation by using more trapezia of narrower width. Have a go at these questions for yourself now, deciding whether your answers are over or underestimates. Remember, your lovely calculators can draw graphs. And watch out with trigonometry, you must be working in radians when you're doing integration or differentiation. Here are the answers. Now we're going to look at a kind of range of different exam style questions. So for this first one, we want to start off by using the trapezium rule to estimate the area A. So we've got lots of information here which is drawn on the graph there. So here we go, let's get our key bits. We need to know where to start and where to finish. So we're starting at 0, ending at 5. We need two strips of equal width, 2.5. Let's quote and substitute into our formula, and then you can use your calculator to make it easier to work out the y values. And you should end up with 10.2. I checked on my calculator, if I do the integral, then it gives me a close answer to that. For the second part, we're going to deduce an approximate value for the area of region B. Well, hopefully you can see that going O5P3 gives us a rectangle. And if we do the rectangle, take away the area we just found out, we're going to be left with our answer B that we want. There we go. And that gives us 4.8. Finally, do we have an overestimate or an underestimate for B? Not for A, but for B. Well, we can see that the curve is curving gradually downwards. If we drew a straight line across, we'd end up with A being underestimated by the trapezia. So that means if we're underestimating A, we must be overestimating B. The easiest way to see this would be to sketch in the trapezia. This is an old exam question. We're going to start by using the trapezium rule. So I've jotted down my key information. So to pop into my trapezium rule, I need to know my limits. So I've got 3 and 5. I need to know my number of strips, which is 4, and I need to know their width, which I don't need to calculate because I've been told it's 0.5. Now I'm going to quote and substitute into the formula. There we go, there's the quote. And when I substitute in, I want to work out my y values, so I'm going to use the sequence thing on my calculator. I've then just calculated using the list with the funny square brackets thing to do that rather than typing in the individual logs, but you can type in the logs if you want to. So you should get 1.55. Right, for part 2, we need to then deduce an approximate value for log of root 2 plus x. So we just need to find a connection. It's a bit like when you're doing your binomial. So, first of all, hopefully you remember that the square root is the same as power half, which means that we can bring that power down in the log, and we already know what that integral is, so we need a half of the answer we got before, 1.55. And there's our final answer, 0.776. I kept all the digits on my calculator from part 1 so that I didn't get rounding error for part 2. Here's another exam question which shows you how they tie in lots of different topics. The first part, we need to sketch a graph. You have a lovely graphical calculator to help you, but you should recognise that it's an exponential graph. You can make up any value of k. In order to be able to not be too steep on my calculator, I used 1.2. We can use anything sensible. There we go. Now, how did I find the coordinate crossing with the y-axis? Simply substituted in x is 0. And we know that it's never going to cross the x-axis, so there won't be an intersection there. Be very careful drawing that bit heading towards the negative x-axis, that you don't accidentally touch the x-axis or curve the graph upwards. For part 2, we're given a y-coordinate and we have to find an x-coordinate. So first substitute into the equation for the curve. We know from the question we're going to involve log base k of 5. So I know I need to take log, so I'm going to simplify what I can beforehand. So I've divided by 4. Right, now we can take log base k, and now we can apply log rules. On the right hand side we can bring the power down. On the left hand side we've got a multiplication, so we can split it into adding 2 logs. Okay, now if you remember, log base k of k is 1, so the right hand side is very simple. And on the left we can bring that power of 2 down, and log base k of k is 1. So there we go, let's write it the way they want it. For the next part, we're going to use the trapezium rule. Let's jot down our key information. Now then, we have got an expression that involves some algebra k that we don't know the value of. So we can't use the calculator to help us work out our y's this time. We simply have to substitute our x values into the formula for y. Now the x values are very simple. We're just going to have 0, a half, and 1. There we go. We know that k to the power 0 is going to be 1. We know k to the power 1 is just going to be k. And we know that k to the power of a half is root k. So there we go. That's a bit nicer. We multiply the 2 and 4 there. And we can quarter everything. And that's our answer. It looks rather simple, straightforward. For part B, we're told that this equals 16, and we now have to solve it for k. So first of all, we write that equation down. And we can see here that we have got a hidden quadratic. I've replaced k with p squared and root k with p. Now we know that it has to be positive, so square root is a positive quantity. For this one, we use our calculators to find out that p is -5 or 3, so that means root k is -5, which we're not allowing. So we'll have root k is equal to 3 instead. So that means our final answer should be k is equal to 9. Here are some questions for you to try. I'm going to reveal the answers now.